Example 1.5.2. Assume a DC power system with a load voltage of 110 volts provides power to a city with 200 lamps, each having a resistance of 220 ohms. The power plant is located a kilometer from the city and is connected via 10 gauge solid core copper wire that has a resistance of 3.28 ohms per kilometer. Determine the generator voltage necessary to supply the load at the appropriate load voltage and determine the ratio of the power delivered to the load to the total delivered by the plant. So this is an example of kind of a DC power system similar to what Edison would have developed. So the givens are best described using a circuit diagram. We've got some sort of generator that's producing a DC voltage, which is delivered to the load via a copper wire. That copper wire will have a lumped resistance associated with it, so we'll represent it as R line. The load is a bunch of lamps. It's a power distribution system, so they're all connected in parallel. There's 220 of those. Individually they have, there's 200 of those, and individually they have a resistance of 220 ohms each. The voltage across any individual lamp by design needs to be 110 volts for them to operate, so that's the load voltage. It's a DC load voltage in this system. And then we need to supply a return line for the current, and so there's another copper wire that's also another 1 kilometer 10 gauge solid core line. So that's our circuit model. We have a little bit more information that isn't included in that model. That's that it's a 3.28 kilometer. Sorry, it's not 3.28 kilometers. That's incorrect there. That's a mistake. It's 1 kilometer, and the resistance is 3.28 ohms per kilometer. When resistance is given per unit length, we always put a prime on it to indicate that it's a per unit length quantity. So what we're asked to find is what is the source voltage necessary to deliver a load voltage of 110 volts, and then what is the total efficiency of the system. In essence, what's the ratio of power generated to power delivered to the load. So the solution method is that what we want to do is we want to simplify our circuit. So we would like to replace the parallel loads with a single resistor, where we calculate the net effect of all of those 200 lamps. And each of them has a voltage of 110 volts on it, and then we still need to include the two line resistances there. So that's step one, and what we'll do is we'll calculate the current in this circuit to find the voltage drop across the line resistances. So we can simplify this circuit a little bit. Since it doesn't matter what order the resistors occur in, we can combine R line and R line into, we can move them both in front of the load, and that doesn't affect the voltage that's dropped across the lamps at all. It's just a rearranging of the circuit, so that's fine. And then what we can do is we can combine those two series line resistances into one lumped element, just 2R line. So this is kind of the simple steps we're going to do to create a circuit model that allows us to analyze this DC system. What we need to calculate next is what the R line is. We know it was a 1 kilometer line, and we know that it was 3.28 kilometers, or 3.28 ohms per kilometer, so the kilometers just cancel there and you get 3.28 ohms for 1 kilometer of line. You'll find out later that there are more advanced models. This is just a simple analysis method. It's called a lumped method. Since there's two of those, we just need to multiply 3.28 ohms by 2. We get 6.56 ohms. Next, we need to calculate the effective resistance of the lamps. Since they're in parallel, we need to use the parallel resistance formula, where 1 over R total is 1 over R lamp 1 plus 1 over R lamp 2, etc., up to 200 lamps. So the denominator in each of those reciprocal fractions is going to be 220 ohms. So since there's 200 elements, it's just 200 over 220 ohms is the reciprocal resistance. And we can calculate total lumped resistance just from 220 ohms divided by 200. You do that, you're going to get 1.1 ohm. So that's going to allow us to redraw our circuit model. And we still don't know the source voltage, so that's just a DC voltage source. We've got a lumped two-line resistance, and then we have our load resistance. The lumped two-line resistance is 6.56 ohms, and the load resistance was 1.1 ohm. We know that the voltage drop across that 1.1 ohm parallel light load was 110 volts DC, and what that's going to allow us to do is calculate the current through that loop. There's only one branch in this reduced circuit, so the I flowing through the load has to be the I flowing through the line. And calculate I just by V over R, so that's 110 volts divided by 1.1. That means the load, the combined load, is drawing 100 amps. That's the total load current. It means each lamp's drawing half an amp. We can also, for later calculations, calculate how much total power is being consumed by those lighting loads. It's just the current times the voltage, so 100 amps times 110 volts is 11 kilowatts. So that gives us how much power is actually delivered to the load. Next, what we need to do is figure out what the voltage drop across the lines was. So in all power systems, there is voltage that is lost in the distribution lines. So we want to calculate that next. What is V line? And it's just going to be the current flowing through it times the resistance. So that's that 100 ohms times 6.56. Sorry, 100 amps times 6.56 ohms. So that's a lot, 656 volts. We can also calculate how much power is lost in this distribution line resistance, and we can just multiply the current through the resistor times the voltage dropped across the resistor. So that's going to be that 100 amps times that 656 volts, which is 65.6 kilowatts. Quite a bit. So now we can calculate what the source voltage is just by Kirchhoff's voltage law. We know that the voltage generated by the voltage source has to be equal to the sum of the load and the line voltages. That's a closed loop. And so that's 110 volts at the load plus the 656 volts dropped in the distribution cable. So we get 766 volts is what the generation voltage necessary to deliver 110 volts to the load is. So amazingly high in this example. One of the major limitations of the Edison DC system. We also pay for power, so let's figure out what the efficiency of the system is. We need to know what the load, which is what our customers pay for, divided by the total, which is how much we paid for as system operators. So 11 kilowatts was the load, and then the total is just the sum of the load plus what was lost in the distribution line, so 11 kilowatts plus 65.6 kW. So that's 11 kW divided by 76.6 kilowatts, multiply that by 100 to turn it into an efficiency in percent, and we get a extremely low 14.36%.